Right, we're going to cover everything there is to know about pulleys in AS. Super important topic going into year 2, so we need to master the basics before next year when we're doing them on slopes and at all various weird angles, okay? So to start with the very basics, the situation is you'll have a pulley with two different particles, and typically you'll know the mass of each particle, and the two unknowns you'll be asked to find will be the tension in the string and the acceleration which the particles experience. Okay, so first we're just going to label all the forces on there. We're going to label tension. Always from the point of view of the particle, tension is pulling upwards, and the weight of each particle as well. So if the mass is 3, weight is 3g, mass is 5, weight is 5g. And what you need to bear in mind is we know which direction each particle is going to accelerate in, right? The heavier block will move downwards. So acceleration downwards for this block, and acceleration upwards for this block. Now we just use Newton's law, right? We do F equals ma, and the really key thing is we just do both particles completely separately. So let's say this first one was called particle A, the second one was particle B. I would say to start with, I'll do particle A. And because it's accelerating upwards, we're going to do our resultant force in the upwards direction. So upwards force is T minus 3g, because 3g is going downwards. F equals mass times acceleration, okay? Then I'm going to go over to B and do the exact same thing. So this time, because B is accelerating downwards, I'll take downwards as my positive direction. So instead of T minus 5g, I'll have 5g minus T equals mass times acceleration. Now, in an exam, this would be called the equation of motion for particle A, and the other one equation of motion for particle B. So just if they ask for it in that specific way. Also in an exam, believe it or not, this so far would typically be 4 marks already. Every single Pulleys question. Just do F equals ma twice, you'll get 4 marks. Quite amazing. Another 1 or 2 available for actually then going and solving the equations. So like I said, typically tension and acceleration will be your 2 unknowns. It's simultaneous equations, so do whatever method you like. If you've done it correct, your tension should always cancel out by adding. You always have a plus t and a minus t. So I'm going to add my equations together. So add. So I'll have 5g minus 3g is 2g. T minus t cancel. 3a, 5a is 8a. Common mistake is writing g equals 4a. Yeah, not wrong, but a is the unknown, yeah? G is a known number, 9.8. A is g over 4 meters per second squared. I'll leave it in terms of g, but you can calculate that exactly if you want. And then we could also go sub that back in to find tension. So tension minus 3g equals 3a. I'm just subbing into the first equation. You can choose your favourite. 3 add 3/4 is 15 quarters. And this will be in newtons. Okay, so that's the basics. Again, possibly 5 or even 6 marks in an exam just for this. One thing you should notice about acceleration, it's always going to be a number which is less than g. Makes sense, okay? Because a particle not attached to any string, not attached to any system, would fall at a rate of g, meters per second squared. So obviously, the particle when it's falling downwards, it's going to be slowed down. It's being held back by the 3 kilogram particle it's attached to. So it has to be smaller than g. Let me just draw a quick one for you to try. Example yourself. I'll do this a couple of times throughout, so I'll do one and then I'll just put a little example for you to try. You can do, or you can just sort of skip, it's fine. So let's say I have the exact same situation. Particles are 10 kilograms, and so that's not very clear at all. 10 kilograms, and let's do 4 kilograms. And again, I just want you to find the tension in the string and the acceleration of the particles. You can leave everything in terms of g. And what I'm going to do, this will be question number 1. I'm just going to pop the answer to question number 1 in the description. So once you've had a go, just check the description there. Hopefully you get all that fine. So we can move on. And that was the basics. Next thing they can add on is a concealed bar. And I'm actually going to illustrate this with the second kind of tension we see a second kind of pulley we see in year 1. So in year 1, most commonly, maybe it's like a vertical pulley, but sometimes also a horizontal pulley, where one block is here on a table, and one block is falling. Same exact principles are going to apply. Let's say it's 3 kilograms, and this one here, this could even be heavier. I'll do 5 again. Same exact idea. I'm going to add tension in a string, which from the particle's point of view pulls it upwards towards that pulley or horizontally towards that pulley. I can definitely add in my weight 3G. And the next part kind of depends. It may be a smooth table. It's a smooth table meaning no friction, meaning as this 5 kilogram block slides to the right, there's no force opposing it. Maybe a rough table with friction. This year, if it is a rough table, which let's say we're going to do for an example, if that's the case, it will just be a constant resistive force. The friction will be a constant, it will be an unknown value, or it will be a value they tell you. Let's say there is 1 Newton of resistive force, constant. Okay? This will be A, this will be B. Now we follow the same principles here. The difference being that on particle A, the weight of the object is not really going to come into consideration. There's no 5G term in my equations, okay? Because particle A, think about which direction it's going to move in. Well, I mean, it doesn't matter that it's heavier than particle B, it's still going to move to the right. Okay, it's not going to move to the left. Particle B is going to move downwards. So because A is moving to the right, I will take my resultant force to the right. T minus that 1 Newton. If this wasn't there, it just wouldn't be here. Okay, it'd be fine. Force equals mass times acceleration. B is actually the same as before, it's moving downwards. So 3G minus T equals 3A. And again, I can add to solve for T. 3G minus 1 equals 8A. In this case, since it's not going to be nice and neat in terms of G, I will just put it in my calculator. 3 times G, take away 1, divide that by 8. We get 3.55 meters per second squared. And let's say the question didn't ask for tension, so I'm not going to go bother doing that, but you could. Okay, so we've seen a horizontal pulley. They can ask SUVAT related questions, so I'm going to add it on here. I'm going to say particle B started, let's say it started 3 meters above the ground. And the question is going to be, say it's released from rest, the system is released from rest, or the particles are released from rest, you could say either one. I could ask the time taken for B to hit the floor. That's going to be my question, okay? So it starts 3 meters above the floor. I didn't draw the floor, let's add that. And I'm going to ask how long for it to reach. Well, we've already got 5 or 6 marks, let's get another 3 more or so. Looking at particle B, we've just solved that the acceleration it undergoes is 3.55 meters per second squared. That is a constant number. So we can use SUVAT, right? Constant acceleration means we can use SUVAT. I would usually say vertical motion you take up to be positive. However, I think it is okay here. Everything is going to be positive if we take downwards to be positive. So we can just do it that way. For simplicity, it's kind of your preference. B is moving 3 meters downwards, starting from rest. So we know the initial velocity is 0. And the acceleration usually would be 9.8 in free fall. We've just calculated the acceleration. It's 3.55. So we're using that acceleration we calculate in our SUVAT. And we are solving for the time. That's the question, right? And okay, yeah, maybe you might prefer to do S equals -3, A equals -3.55. Up to you. As long as we're consistent here, downwards being the positive direction, so both displacement and acceleration are positive. S, U, A, and T is going to be S equals UT plus 1/2 AT squared. So begin with U equals 0. and then just use my calculator here. So 6 divided by 3.55, and then square root of my answer. And taking the positive solution, I make that 1.3 seconds, almost exactly. Okay, this is a basic kind of SUVAT. I've only done one SUVAT. We'll see later you have to do 2 different SUVATs on a situation. Just a quick note before we get onto that though. Quite a common misconception about this value of V. What does this represent? I'm actually going to come to calculate this in a minute. Some of you might have been saying, when I set my SUVAT, that V should be 0, because V is the final velocity, and after the particle hits the floor, well, it's not moving. That's not correct, okay? So V represents the velocity with which the particle hits the floor. How fast is it moving? Fraction, of a second, like an instant, right before it hits that ground. How fast is it moving? That's what V represents. As soon as particle B actually hits the floor, that's an external force coming in from the ground. That messes up this whole constant acceleration assumption, right? And the whole SUVAT equation is no longer valid. So V is how fast it hits the floor with. V equals 0 is typical of something being instantaneously at rest. For example, a particle being thrown in the air and accelerating downwards, but at the very maximum height, just being stationary. So V will be the speed at which it hits the floor with, and quite often we'll actually need to calculate this. So that's quite a lot of information. Before we do any more, I'll give you a quick one to do with yourself. This will be question 2. And again, I'll just pop the answer down in the description. So question 2. Let's do this one as a horizontal system as well, just so you can practice that. We'll just say 5 kilograms here. We'll say 8 kilograms here. We'll say it's 2 meters off the floor. So my question will be, what is the acceleration? And then what is the time taken for particle B to hit the floor? And in this question, I'm not going to have any friction acting here, okay? So you won't have this takeaway 1 term. There's going to be no friction action, right? It's a smooth table. Also, this is all assuming that particle A is not hitting the pulley and messing it up. That's going to be an assumption in the question. Okay, so answering the description for that one. Let's move on and do the sort of hardest type of question, which is a 2-stage SUVAT. And I think I'm going to illustrate this first with a vertical setup. I think it's maybe slightly more straightforward. Kind of up to you which one you find easier. So we'll go 10 kilograms. We'll go 5 kilograms, nice and simple. Add on the tension, add on the weight. And very quickly, again, what I'm going to do is just calculate the acceleration. So particle A is moving, A is heavier, A is moving downwards. B is lighter, B is going to move upwards. So A downwards, 10g minus t equals 10a. On B, B is moving upwards, so I'll do t minus 5g, 5a. Adding together, 5g equals 15a. Perfect. A is g over 3 meters per second squared. Okay. A typical question which is in exam requires 2 different SUVATs, as I said, because it might ask something like, what's the maximum height that A reaches, that B reaches in this motion? So let's say A starts 1 meter above the ground, and B maybe starts half a meter above the ground. And I will say, what is the maximum height reached by B in the subsequent motion after the particles are released? Maximum height above ground. And an assumption in this question will be that the particle B is not going to hit the pulley and get in the way. The pulley is high up enough that it doesn't affect anything. Okay, why is this tricky? Well, you've got to think about what's going to happen. I'll try and draw this out as best as I can, but particle A is going to move down and hit the ground. Move down 1 meter, which means particle B will move up 1 meter. It's going to be an inextensible string, so whatever A does, B does, but just kind of reversed. Let's draw that first stage on now. So this is sort of stage 1. It's going to be a very minimal diagram. A on the left, B on the right. So in the first stage, it's going to be A from where it is to the ground, and B will come up a little bit. Okay. During this time period, it's constant acceleration, right? We just calculated that A will actually move downwards with acceleration g over 3, and B will move upwards with acceleration g over 3. That's fine. But particle B doesn't just stop there, right? When A hits the floor, the tension in the string will go away. B will stop accelerating upwards, but it was moving upwards with some velocity. It has momentum. It's going to continue going up under its own momentum, right? It's like if you are holding the ball and you start with your hand really low and you raise it higher and higher and higher, and eventually you stop moving your hand. The ball won't remain in your hand. It will carry on going. You've given it some upwards velocity, right? So this block B, now in the second section, it will always say this assumption as well. A will remain on the floor. It won't bounce. Whatever. Just keep keeping everything nice and simple. Block B will continue to rise. The string will go slack. It's going up and going down. So in this section, what's the key guiding principle that will help us calculate? The guiding principle will be no tension. There'll be no tension in the string anymore because it's gone slack. It's not pulling on the block anymore. In this specific context of a vertical pulley, what does that mean? Well, if you look at block B and you imagine cutting tension out of the equation, there is only one force acting on it, and that is its weight under gravity. Well, when there's only one force acting on an object, which is its gravity, and in that case, that's just a free fall under gravity question. It's a Suvat question. The acceleration will be negative g. It's accelerating downwards 9.8 meters per second squared. Just like any Suvat question you've done with free falling particles, or particles moving freely under gravity. So I need to do one Suvat equation for this process here, as B lifts that first 1 meter, and then a second Suvat as B moves a little bit further. And the question is, like, how far does it move? So typically there might be one or two things you need to calculate during this first Suvat. You're almost always going to need to find the final velocity of the particles as they move, till you can find the instantaneous velocity that B has right here, right as A hits the ground. Okay. So we'll answer in this example. During that first stage, where A moves 1 meter downwards, you can do a Suvat on either particle A or particle B. Again, they're the same motion. Our particles are moving 1 meter, starting from rest, and the acceleration we calculated was g over 3. I wrote that down in red, g over 3. And what we're going to need is that final velocity. That's the key. So v squared equals u squared plus 2as. I'll just type my calculator. So u is 0, so square root of 2 times g over 3 times by 1 meter. 2.56. And we're going to write down a few decimal places, just because that's not my final answer yet. I don't want to get any rounding errors. So after block A falls 1 meter, or after block B rises 1 meter, its velocity is 2.55. That's how fast it's going at this exact instant, which means when I do my second Suvat, that final velocity will now become my initial velocity. Right? The final velocity of the first period is the initial velocity of that second period. They're right after each other. The next period, SUVAT. V u is now v, and the acceleration is now downwards, negative 9.8. Okay, it's block B, it's falling under gravity. And now it just depends on what the question is asking, right? So this question is asking how high above the ground, right? What's the maximum height achieved right here? So I'm going to be interested in the displacement. And I know when I've got an object and I want its maximum height, I can set v equals 0. You should have learned that during SUVAT. So again, it's going to be v squared equals u squared plus 2as. So let's see, 0 equals this number squared minus 19.6s. S is going to be square this and divide by 19.6. Oh, 1/3. Brilliant. Okay. So what we've learned is during the second period, during free fall, particle B rises an additional 1/3 meter in the air. Now, final question, how far above the ground does B reach, right? What's the maximum height above ground reached by B? Just adding up all our stuff, right? So B started 0.5 meter above the ground. That's important. During the first SUVAT period, it raised 1 meter, so becoming 1.5 meters above the ground. And then it gained an additional 1/3 of a meter. So I'm going to do 1.5 plus 1/3, and that's some number with a 6 in it. 11/6. 11/6 meters above the ground. So that's my final answer. Okay. So I've just added up how far did it go during that first SUVAT, how far did it go during that second SUVAT, and then also an additional 0.5 because that's what it started above the ground. So I hope that's kind of clear. It's really hard to draw without a physical demonstration, but I will do one more example very quick, just to sort of reiterate, and then I'll write a couple for you guys to try. So this one's just going to be a horizontal one, and I'll use the numbers from before to speed things up. So we had 5 and 3 and 1. In fact, no, I will do a different one. For a reason you'll see in a minute. We'll do 6 and 4. These are kilograms, so I have 4g. I have tension. Again, I'm going to have a smooth table. We'll talk about how it would look like if it wasn't a smooth table. But I think this is an important example to see. So particle A, particle B. On A, I will do resultant to the right, because it's moving to the right, accelerating to the right. So it's tension minus no resistance equals mass times acceleration. On B, it's accelerating downwards, so 4g minus tension equals mass times acceleration. Adding together, 4g equals 10a. A is 4/10 or 2/5g. Fine. So this question is going to be slightly different. I'm going to say that B lies 1.5 meters above the ground. A lies 5 meters away from the pulley. And I'm going to ask the time taken for A to reach the pulley. That's the question. Again, you can hopefully recognize a two-step SUVAT here, because for those first 1.5 meters that A moves, it's going to be being dragged down by particle B. And then for the remaining 3.5 meters, it's not, because B is going to hit the floor. So first 3.5 meters, what can we say? Well, why did I say first 3.5? I meant first 1.5. That makes more sense. Well, I've just calculated. A is going to accelerate to the right 2/5 g. All these values will apply to both A or B. It's going to start from rest, and it's 1.5 meters. So I have a choice. I can either calculate V or T. And once I've got 3, that's enough to calculate a fourth. Well, we're definitely going to need T, because we asked how long does it take for A to reach the pulley. So I think that's S equals UT plus 1/2 AT squared. S equals ut, which is 0, plus 1/2 a t squared, which is this, 1.5 divided by 1/5, so times by 5, divided by g, and square rooted. I get 0.8748. You definitely need t. You also, like I said, you most always need v as well. So v equals u plus at, or v squared equals u squared plus 2as. Doesn't really matter. So square root of 2 times 1.5 times 2/5 g. What do we get? 3.4 v equals 3.4293. Okay. So after 1.5 meters, we know how fast A is moving, or how fast B is moving, and how long it's taken to get there. Now, the second 3.5 meters. This is important. How do we deal with it now? It's not going to be like before, a free falling particle in the gravity, right? A is not moving vertically. B hits the ground and doesn't bounce. A will continue sliding to the right. Now, what happens to it? Well, there's no tension. There's nothing pulling it forwards. And there was no friction. It's a smooth table, so there's nothing pulling it backwards. So actually, no forces are acting in the horizontal direction, meaning there's no acceleration. It's constant velocity. It's going to stay at the same speed until it hits that pulley. Now, if it was a rough table, you'd have to add in your friction or your resistive force, and it would actually decelerate. You'd calculate F equals ma, calculate the deceleration, and you basically put that in as a negative a, and the particle will slow down eventually, and you can calculate whatever with it. In this case, though, no forces, no friction, no tension, no acceleration. So with no acceleration, you can just use speed equals distance over time, because velocity will be constant. See if that works just fine now. Okay, initial velocity u is a v from before, like we had, 3.4293. And it's traveling another 3.5 meters. I'm interested in how long does that take. Well, again, I'll do s equals ut plus 1/2 at squared. A is 0, so just s is ut, or 3.5 equals 3.4293 t. T equals 1 point something, right? 1.021. So 1 and a bit seconds for that second part of the journey, just under 1 second for that first part of the journey. Adding those together, plus 0.875, 1 answer plus 0.875, 1.896 seconds. Okay. So again, I split up into two different superbaths. How long did that first section take? What's the velocity after that first section? I need that for you for the second section. And in the second section, what's changed is there's no tension, so my forces, there's no forces now, constant velocity. Okay, so let's just try a couple. I'll draw out a maximum height question. So I'll have a particle, let's do 1 kilogram, let's do 2 kilograms. Let's say the 2 kilograms started half a meter above the ground, 1 kilogram started 1 meter above the ground. Out the max height, A and B. The maximum height above ground reached by A. That'll be my first. This will be question number 3 now. The answer will come in the description. And let's do one more on the challenge, so question 4. It can be a similar situation to what we just had, so you can go back and watch it again. It'll be a smooth table with no friction. It'll be 2 kilograms, it will be 6 kilograms, and the question is going to be, if this is 2 meters, and this is, again, let's do 5 meters. I want the time taken for A, this would be A to hit the pulley, to reach that pulley. And if you wanted a little, well, I guess it's a challenge because I haven't shown you directly how to do it, but you should be able to use the same principles, and we did sort of talk about it. We'll do a rough table where there's a constant, let's say 0.2 G resisted force to motion. We'll have the same weights as before. Let's say this is 2 meters, 6B. And what we'll say, how far does A move from a starting position until it stops? So what we'll assume is that the distance from A to the pulley is very large enough that A will never hit the pulley. This friction will slow it down and stop it before it hits. So my question is, how far in total does A move before it's stopped by its own friction? So 2 meters and then a little bit extra. Okay, so in this bit, remember, like we talked about, there's actually going to be a deceleration after this particle B hits the ground. Right, so answers on the description, so go and check them. Let me know how you do, if there's any questions, and learn this really well over the summer, and you'll be ready for year 13.